Touchdown on the Moon. A lunar lander is making its descent to Moon Base 1 as shown in the figure. The lander descends slowly under the retro-thrust of its descent engine. The engine is cut off when the lander is 5 meters above the surface and has a downward speed of 0.8 meters per second. With the engine off, the lander is in freefall. What is the speed of the lander just before it touches the surface? The acceleration due to gravity on the moon is 1.6 meters per second square. So this lunar lander will have a velocity as a function of time, which is given by its velocity when the engine was cut off, v0, minus the gravitational acceleration on the moon times t. It's going to be constant acceleration motion again. And it has a downward speed, so it's negative, 0.8 meters per second. So this is minus 0.8 minus the gravitational acceleration was 1.6, so it's minus 1.6 t. And this is going to be equal to the rate of change of its position, dy dt. So the total displacement we have in time interval 0 to t would be the integral v of t dt from 0 to t, which is the integral from 0 to t minus 0.8 minus 1.6 t dt. So the displacement we have on the y-axis in the time interval t, delta y as a function of t, will be minus 0.8 t minus 0.8 t square, because it's 1.6 t square divided by 2, so 0.8. And at the final time, t equals tf, it touches the surface. So the lunar lander will touch the surface. Okay. Now, if I evaluate the total displacement on the y-axis, delta y, at time t equals tf, I will have minus 0.8 tf minus 0.8 tf square. And what is this displacement? We're going from plus 5 meters to 0 meters, so displacement is minus 5, 0 minus 5, so it's minus 5 meters. And therefore, we find that if we divide both sides by 0.8 and take the time to the right-hand side, we're going to have t final square plus t final minus 6.25 equals to 0. So I have divided this equation by minus, so I've taken the time to the right-hand side and divided it by plus 0.8. So this gives me, for the fall time, tf, minus 1, because I have a quadratic equation, minus b, plus or minus, we're not going to take the negative root, plus square root b square minus 4ac, so it's 1 square plus 4 times 6.25 divided by 2a, which is 2. So this gives me minus 1 over 2 plus 1 over 2 times square root of 1 plus 25, and that will give me 1 over 2 parentheses square root 26 minus 1. So the velocity that I will have at this time, at the fall time tf, will be v of t evaluated at tf minus 0.8 minus 1.6 times 1 over 2 square root 26 minus 1. That's the time. So that gives me minus 0.8 minus 0.8 square root 26 minus 1, which is in minus 0.8 parentheses minus 1. So it's going to be plus 1 plus square root 26 minus 1. So you can see if you distribute here, you will get minus 0.8 and minus 0.8 parentheses square root 26 minus 1. So I find that the final velocity, VTF, will be minus 0.8 square root 26. So this plus 1 and minus 1 will cancel, which, if you evaluate, is found to be minus 4.1 meters per second. I checked the number of significant figures. It's 2 here, so it is reduced to 2 significant figures, minus 4.1 meters per second. All right, so the minus sign indicates that the velocity vector is pointing downward. Because of the minus sign. All right. Now, alternatively, going back to my velocity equation here, v of t equals v0 minus gm times t, I could write t is equal to v0 minus v divided by gm, the gravitational acceleration on the moon. And with that, delta y of t is equal to v0t minus gm over 2t square when I integrate v of t dt. This is what I find here. Basically, this is what I have done here. v0t minus gmt square over 2, that would be the integral from 0 to t. And this will be equal to v0 times, for t I substitute v0 minus v divided by gravitational acceleration on the moon, minus gm over 2 v0 minus v square divided by gravitational acceleration gm square. So this square will get rid of this gm, and I'm going to find, if I multiply both sides by 2gm, 2gm delta y of t is equal to 2v0 square minus 2v0v. So basically I'm multiplying this by 2gm, and then I have minus v0 square plus 2v0v minus v square. So if you open this up, you get v0 square minus 2v0v plus v square, but because of the minus sign here, this is what we will obtain. And with that, we're going to have a cancellation, minus 2v0v and plus 2v0v. So this will give us 2v0 square minus v0 square is v0 square, and then I have minus v square. So I obtain v square is equal to v0 square minus 2gm delta y. Okay, so I take v square to the left hand side and this one to the right hand side. And with that, v becomes square root, the speed is going to be given by v0 square, square root of v0 square minus 2gm delta y. And for the final velocity, you have to be careful because it's coming down, so the velocity vector will be pointing downward. Anyway, the question was, what is the final speed? The speed just before it touches the surface. The velocity is minus 4.1, the speed is 4.1 meters per second, which could also be found by using this relationship between velocity and position. So this gives me a speed of 4.1 meters per second. Okay, so to summarize, we had a lunar lander. It was coming down with a downward speed of 0.8 meters per second. When it is 5 meters above the surface, the engine is cut off, so it has an initial speed 0.8 meters per second. Under the influence of lunar gravitational acceleration, it is coming down to touch the surface, which is 5 meters away from where it currently is when the engine is cut off. So the velocity is v0 minus gmt. It is the constant acceleration motion, and at time tf it touches the surface by traveling a distance 5 meters, so delta y is minus 5 from where it started to where it ends, and delta y is related to its velocity as a function of time, integral 0 to tv of t dt. So using this relationship we can solve for the fall time, and we can evaluate the velocity at the fall time, find minus 4.1 meters per second, pointing downward because of the minus sign. The final speed is 4.1 meters per second, which was really the question that was asked. It's the magnitude of this final velocity. And then we have shown that we could also use the relationship between velocity and position directly without going into this time calculation by noting the time velocity relationship t is equal to v0 minus v over gm, and integrating v of t dt, we have v0 t minus gm over 2t squared, and we can eliminate t by substituting this, and we obtain this relationship. If you plug in the numbers, that would directly give us the final speed of the lunar lander.